Hello and welcome back to the CCNA journey with me, Ryan. And in this section, we're going to continue with the network fundamentals, reviewing public, private, and reserved IP addressing. And then we're going to look at the big picture. Where does private IP sit? Where do public IP sit? And how does the communication between them happen? It's important that you've gone over the previous videos where we've discussed IPv4 and subnetting, so this makes a bit more sense to you. For those who don't know, you can contact me here on YouTube, connect with me on LinkedIn, follow on Twitter, or message on Facebook. Okay, let's get started. Okay, so first let's have a discussion around the difference between public and private addressing. First of all, public. Now, public IPs are leased to users, and they're normally leased to a user or company through what we call an ISP, an Internet Service Provider. And they're the company that you would go to as a consumer or as a business to essentially have some kind of internet connectivity. Now, 9 out of 10 times, this is where the IPs are assigned from, and those IPs are given to you from your ISP. It is possible that those IPs can also be obtained not through your ISP, but actually you can own some IPs, and they can be registered to you as a corporation, and then you advertise those IPs to your ISP, and they give you internet connectivity on your behalf, and we'll get into how that works in a moment. For now, I want to keep it simple, and I want to give you a very basic overview as far as a consumer is concerned. Now, if you can have a think about the internet of how it is today, and you pay for your internet connection from your internet service provider, whether that's someone in the UK like British Telecom or someone in America like Time Warner, essentially you pay a monthly fee to have this internet, or essentially connection to the internet. And every time you turn your router on, they're going to lease you an IP address, whether this is going to be static or dynamic. That IP address, again, is globally unique to you. No one else can use the IP address. And the reason for that is because when packets at layer 3 are built and sent out towards the internet, obviously everyone on the internet connects, and they have to be unique in order for the traffic to get back to the correct source and to reach the correct destination. Now, these IPs, like I said, can be static or dynamic. Now, essentially what this means is static refers to you always obtaining the same IP address. So let's say, for example, the IP address you've obtained is 82.100.110. Every time you turn on your router, that IP address will be assigned to you. Dynamic means when your router is turned off or after a set period of time, there's most likely a pool of IP addresses that your ISP keeps, and every time you turn your router on, you will be just giving at random one of these IP addresses in the pool. Now, the reason you might want a static IP address is if you have some sort of hosting. Let's say, for example, maybe you have like an email server. Maybe you like to do something like remote desktop into your PC from a remote location, and you always want to know what your IP address is so you can connect to it. Then there are some of the reasons why you might want a static IP. Now, the reason not everyone has a static IP is simply because there's not that many IPs, and it's easier for an ISP to keep a pool of IPs reserved, ready for when users want to come online. And this method allows ISPs to save on IP addressing. Sometimes you may see with static IPs that they're actually chargeable, whether that's a single /32 host IP range, or whether it's a larger, let's say /29 range, which is 6 usable. Those IPs are then essentially leased down to your router, and then you can configure them beyond, maybe on a particular server, or configure it against a particular PC. If you require something even larger, maybe like a /24, which is 254 usables, sometimes you've been asked to fill out some sort of justification form because the ISP requires you to actually justify why you need so many IPs and why you can't use technologies like NAT to achieve your goal. Like, for example, if you wanted to give every single PC on your network a public IP address, that's most likely going to be declined, because ideally you should be using some sort of NAT, or in this case PAT, port address translation, to actually allow multiple private IPs to NAT to a single public IP sometimes referred to as NAT, sometimes referred to as something called overloading. That is public IPs. They're leased to individuals, they're globally unique, they can come in static or dynamic form, and you can have anything from a single to as many IPs as you can justify to your ISP. They can be obtained from your ISP, which is most of the time where you will be, especially for consumer. However, if you're a large corporation and you want your own IP addressing, you can go to a registry and request those IPs. And therefore, because your ISP do not give you those IPs, it's your responsibility to work with your ISP to essentially advertise those IPs to the ISP for them to advertise onwards to their transit providers. So an example of why you might want to have some public IPs rather than using ISP IP addressing, well, there's two main reasons. One is called multihoming, and the other is referred simply to not being tied down to a single ISP. So let's say, for example, you're a very large corporation and you require a /25. Let's say, for example, you decide to have the internet through two different suppliers to add some sort of resilience into your network. Now, because they're two different suppliers or two different ISPs, they would have been given two completely different IP ranges from the registries. And we'll get into the registries in a bit more detail shortly, or where these IPs actually originate from. But this /25 essentially can't be advertised to you from both ISPs because not both ISPs can own the same /25. So what we can do here is we can what's called multi-home, and essentially we, as the network provider and owner of the IPs, can actually run a routing protocol with our ISP. We normally run something called BGP, which is the Border Gateway Protocol, and essentially we can advertise this /25 to both ISPs, and the ISPs on our behalf can advertise it to the internet. Now, because we give permission for these two ISPs to advertise it on our behalf, already what we've got here is two resilient links downstream back to our network through two different providers. Because it's our /25 IPs and none of the ISPs actually own them, what we can also do is if an ISP in the future, let's say we don't agree with their customer service, agree with their company, what we can also do is actually move those IPs away and go with a different ISP and again advertise those IPs through the new ISP. Whereas if we were to get an IP leased from an ISP, if we were to move away from the ISP, we'd have to give those IPs back. And that's the benefit of essentially owning your own IP range. Okay, so IP addresses which can overlap and assign to internal devices are private IP addresses. Each unicast class, remember we talked about the 5 classes, A, B, C, D, and E. Well, A, B, C, the ranges that are essentially handed out as usable IPs on the internet. Well, each class has got a private IP range, which we'll show in a moment. And I've also got a comment here, which is what would happen if I tried to route or advertise a private IP. Well, first of all, let's have a quick discussion about what private IPs are. So if we think about what we have today, we have our consumer, we have the internet, we lease the internet to a router on the edge of our network, and most likely in your home environment, you just have a single device that doubles up as a router, a switch because it's got multiple ports on the back, and probably offers you some sort of Wi-Fi. Now, if you look at all your devices that connect both wired and wirelessly, you'll notice that you'll probably have an IP range in the 192.168 range, and it's probably a /24. And the reason for that is because this here, 192.168/16, so the first two octets being 192.168 and the last two octets being anything we wish, this is the Class C private IP range. This means that all your devices, your smart devices, your tablets, your PCs, wherever they may be, they will automatically obtain through a protocol called DHCP, the Dynamic Host Configuration Protocol, a IP address inside this private IP range. And essentially the reason for that is because each device, as we know, has what we call a NIC card, a network interface card, and this network interface card requires an IP address to communicate both locally within the network and globally outside the network. And this 192.168 essentially allows communication between devices on your network and allows these devices to communicate to the router, which in this case is their default gateway, and their default gateway to the internet. So for example, if you wanted to go to Google or YouTube, these devices would notice it's not inside their network, as in it's not on the 192.168 network, and it will route towards their default gateway, which is the router, and the router will route towards the ISP. Before routing it towards the ISP, it performs that NAT function that I previously talked about, which is essentially taking these 192.168 IPs, so these private IPs, and it translates them into these public IPs, which means that essentially this interface here, which is public facing, is normally a single IP, and all your devices, let's say you've got 100 devices, because we have a /24, because there's 254 IPs. Let's say you've had 100 devices, you've got a few kids, they've got laptops, you've got iPhones, PCs, laptops, whatever it may be, and they all connect and they all translate to a single IP address. So traffic that's out on the internet, when it needs to return, it will return to this IP as a destination, and your router will be clever enough to keep what's called a NAT translation table to know which device requested which information. And essentially these IPs can overlap, meaning your next door neighbor, the next company, wherever it may be, they too can also use this 192.168 IP range because it's contained within your premises. It doesn't go out to the internet. Now, if you were, let's say, a large corporation and you have some sort of lease line or Ethernet connectivity directly to the ISP, and you have what we done earlier, which was advertising your own public IPs, and let's say you're using that Border Gateway Protocol, BGP, and you accidentally started advertising this 192 range, or maybe the 172 range, which is the Class B, or the 10 dot range. Normally what would happen is your ISP would have filters on the inbound interface that would essentially drop this session to you to prevent those IPs from leaking into the ISP and then onwards towards the internet. Because these IPs are private and they should remain private within a premises or within a network. That's why they can overlap. And essentially, what would happen if you tried to route them or advertise them to an ISP? Well, first of all, depending on the access technology, for example, if you have some sort of DSL connectivity or maybe some cable, then it's probably not possible for you to advertise some connectivity in because you don't have any peering or adjacency with the ISP. But if you were running something like BGP or OSPF, maybe even RIP, then it would be possible for you to advertise an IP that is probably going to essentially cause the ISP to cut off that link to you until you stop advertising it. Okay, so last on this slide, what public and private IPs exist and where do I get them? So in the next slide, I'm going to talk about public IPs and where you would go to actually request IP addresses for your corporation. And then we're going to jump into what's called a RFC, a request for comments, and where the private IPs originated from and why everyone knows what IPs to use on the internet and what IPs to use inside a private network. Okay, so public IP addressing. Now, essentially the IP addresses are handed out in a hierarchical form, and at the top of the tree, there's the IANA, the Internet Assigned Numbers Authority, and it's their job to handle a database of all the public IP addresses, and not just IP addresses, things that we've discussed previously, like the well-known port numbers, they're also held and assigned here. IANA controls both the IPv4 and IPv6 addresses, and again, like it says there, they're assigned in a hierarchical manner. Users are assigned IPs normally by their ISP, which is what we just discussed, And ISPs normally get their IPs from local internet registries, LRI, or national internet registries. But more commonly, IPs are assigned from the Regional Internet Registry, the RIR. You can see from the map just below, different registries covering different areas. So for example, me in Europe, which in the United Kingdom, I would go to RIPE, and I would request some IPs directly to RIPE if I wanted to have my own IP range, and then have my own IP range. Like I said previously, that gives you the ability to advertise it to multiple ISPs. Or if I wanted an IP from my ISP, because maybe I don't justify having a large block of IPs, or maybe I don't necessarily care about having some IPs that are assigned by the ISP because I don't want the hassle and to actually obtaining the IPs. I don't have the knowledge to run a protocol with my ISP. So the ISP themselves would then go to RIPE or wherever it may be in the world to essentially get their public IPs to then hand further down to their customers. Now, unlike public IPs, which require a central authority to essentially manage the uniqueness of them on a global scale, private IPs are designed to be the complete opposite. They're actually designed to overlap in some space, and they're not assigned to anyone individually. In fact, what happens is the IETF, the Internet Engineering Task Force, created a standard, and that standard is called an RFC, and particular RFC relating to private addressing is 1918. And essentially, for those who don't know, an RFC stands for Request for Comments, and essentially a request for comments is a documentation that you put forward as an individual, a corporation, or as a member of the IETF that other people comment against and feedback against. And once it's gone through a couple of revisions, it becomes a permanent authority, a permanent documentation to relate back to. And this documentation of RFC 1918 outlines the private address space, explaining that the 10./8 range is a private Class A IP range, and a 172.16 to 172.31, which is a /12, is a Class B private IP range. The 192.168/16 is a Class C private IP range. Internet Assigned Numbers Authority reserved these IPs, so these will never be global IPs, and they reserved them for private use. And the IETF created an RFC to outline this specification and make it essentially a standard. Now, other RFCs exist. In fact, there's thousands of RFCs, and protocols that we'll speak about throughout this course, such as RIP, TCP, IP, almost every protocol you can think of will have an RFC against it. And if there was any true source of information of how a packet should look or how a protocol should operate, the RFC will essentially outline it in detail. Okay, so moving on to the reserved IP ranges. So just a few special IP addresses that I've not spoke about. First of all is the APIPA, which is the Automatic Private Internet Protocol Address. And essentially it's a 169.254 anything. So the last octets can literally be anything. So it's a /16. And essentially this APIPA is normally only seen on Windows devices, but I have seen it on other operating systems. It's an IP address you would normally see when a device tries to obtain an IP address through the Dynamic Host Configuration Protocol, DHCP. And if it fails, it normally assigns itself an IP address in the 169.254 range. And the next one is the loopback address. The loopback address is part of a 172.000/8 range. Most likely you're going to see it as a 172.001. And essentially what a loopback does is if you open up your command prompt, which I'll do now, and bring it across, and if you were to ping the 127.001, you'll notice that it would get a response. And essentially what we're doing there is we're testing my TCP IP stack against my NIC card. So if you believe that maybe TCP or IP is not working as expected on the particular device that you're on, you can ping yourself. Now, for those who don't know what ping is a troubleshooting protocol that's part of the ICMP stack, which we'll get onto a lot later in our video series when we talk about troubleshooting. What we're doing here is we're asking the PC, we're asking the NIC on that PC, have you got the right software installed? And if someone were to send you traffic, are you going to respond and process that traffic correctly? Next, we have the default or unknown address, and this is the 0000. Now, if you're doing, again, let's say DHCP, when you initially request that IP, so you send out what's called a discover, your source IP is essentially going to be 0000 because you have no IP address to put as a source inside that packet. 000 is also known as the default. So when we look at a routing table and we see a bunch of routes, so for example, if I look at the routing table of my PC, and to do that I type in route print, you can see it will print up a routing table. And looking at this routing table, you can see here are all the routes that my device is aware of, and this is their subnet mask. We can see that there's the next hop and what interface it would go out on. But just at the top, you can see 0000 with a net mask of 0000 and the gateway of 192.168.128.1. If I'm trying to go to a destination that's not in my routing table, it'll be captured by this 000 route and it'll be sent to whoever this 192.168.128.1 is. And it will be sent out the interface that has the IP 192.168.128.3. So essentially it will be sent to my default gateway, which in this case is my router. Okay, so finishing up, let's talk about the big picture. Let's go back to drawing our internet. On the back of the internet, we'll have a lease from an ISP. The ISP will lease us a public IP address. If we were a large corporation and we didn't want to lease a public IP address because we want provider independent IPs, and that's what we call IPs that are not leased for an ISP, we would go to the registry, the Regional Internet Registry, and they would give us an IP address. And we would own those IPs, and instead of the ISP giving us an IP address, we would advertise the IP range to the ISP and expect the ISP to advertise them out onto the internet. So public IPs are globally unique. They can be static, they can be dynamic, and they can be either ones that we own or one that an ISP owns. Behind the router, we tend to have a bunch of devices. These devices will have IPs part of the RFC 1918, which, let's say for example, maybe the 172.16.00/16 range, and that means that all of our devices will have an IP address of something like 172.16.01, 172.16.02. Maybe we have wireless and there's a mobile out there and that's getting 172.16.03. All of these IPs, because they're all private IP addresses, they need to be translated, and the protocol we use to translate them is NAT. A variation of NAT that we're most likely going to use is something called PAT, which is the port address translation, and I'll get into a lot more detail later when we start configuring NAT and PAT and the differences between them. PAT is also sometimes called overloading, and the reason it's called overloading is because we're putting a bunch of private IP addresses on a single public IP address. This is where the term overloading originates from. The reason we need to have a global unique IP address is because all the devices that we need to contact, maybe it's Facebook, maybe it's YouTube, they all need to know how to get back to us. And how do we make ourselves unique to anyone else? We have to have that unique IP that's assigned and managed by the internet registries. Okay, so that's all we've got time for in this lesson. Just to recap on what we've discussed, we had a brief overview of the differences between private and public. We said that public IPs had to be unique, and it's up to the Internet Assigned Numbers Authority, IANA, to essentially hand out a set of IPs in a hierarchical format to people like the regional internet registries, who in turn will hand them out to ISPs or corporations who require their own IPs, which we said were independent IP addressing or provider independent. We said that unlike public, who relies on the ability to be unique, private IPs were originally designed to overlap, and the IANA sort of assigned 3 ranges inside class A, B and C for the private IP range, and this was documented in the RFC 1918 by the Internet Engineering Task Force, and we had a quick overview of what is an RFC and who are the IETF. We then briefly talked about NAT and PAT. We said that NAT is a translation method that's used on routers to essentially translate IPs from private to public. So we only can have one public IP but multiple private IPs, helping with the lack of public IPs that we have. And then we put it all together at the end in a big picture and kind of seen how it all fits together. I hope this video has been informative and I'd like to thank you for viewing, and if it has been, please do like and subscribe.